Hello sir, myself D. Kiran Sai Kumar and I am from EC department. So my topic in CAA2 is state equations. So first we can see introduction to state equations. State equations are mathematical representations of dynamic systems. They describe the system's behavior in terms of state variables. These equations are crucial for analyzing and designing control systems. So these state equations are mathematical representations of dynamic systems, and these are used to this can describe the system's behavior in terms of state variables, and these equations are very important and crucial for analyzing control systems and designing control systems. So this is the introduction to state equations, and now we can see the state equations. In state variable information of system consists of input variables u of t, output variables y of t, and state variable x of t. So in the standard mathematical form of the system is expressed as a set of n coupled first order ordinary differential equations known as the state equations, in which the time derivative of each state variable is expressed in terms of the state variables x2 of t and so on xn of t, and the system inputs u1 of t and so on ur of t. In the general case, the form of the n-state equations is I1 equals to f1 of x comma u comma f, and that is x1 dot equals to f1 of x comma u comma f, and x2 dot equals to f2 of x comma u comma f, and xn dot equals to fn of x comma u comma t, and in vector notation the set of n equations in equations 1 may be written as x dot equals to f of x comma u comma t, where f of x comma u comma t is a vector function with n components. F1 dot of x comma u comma t, and here x1 dot equals to a11 x1 plus a12 x2 plus and so on, a1n xn plus b11 u1 plus and so on b1r ur. X2 dot equals to a21 x1 plus a22 x2 plus and so on plus a21 xn plus b21 u1 plus b2r ur, and so on x dot n equals to an1 x1 plus an2 x2 plus and so on ann xn plus bn1 u1 plus and so on plus bnr ur, where the coefficients aij and bij are constants that describe the system, and now we can here take a derivative d by dt of x1 x2 and so on xn equals to a11 a12 and so on a1n a21 a22 and so on a2n an1 an2 and so on ann into x1 x2 xn plus b11 and so on b1r b21 b2r bn1 and so on bnr into u1 ur, which may be summarized as x dot equals to ax plus bu. The above equations are in the form x dot equals to ax plus bu. Here d by dt of x1 x2 xn is the x dot, and a11 a12 a1n a21 a22 a2n an1 an2 ann is the a, and x1 x2n is the ax. So these are ax plus b11 b1r b21 b2r bn1 bnr is b, and u1 ur is the u, which is in the form of bu. So the above equations is in the form of x dot equals to ax plus bu, and where state vector x is a column factor of length n, the input vector u is a column vector of length r, a is an n into n square matrix of the constant coefficients aij, and b is an n into r matrix of the coefficients bij that weight the inputs. And here the output equations is a system output is defined to be any system variable of interest, and arbitrary output variable in a system of order n with r inputs may be written as y of t equals to c1x1 plus c2x2 plus and so on plus cnxn plus d1u1 plus and so on plus drur, where the ci and di are constants. If a total of m system variables are defined as outputs, then the output equation can also be obtained as state equation in compact form y equals to cx plus du. And the above equation is in the form of y equals to cx plus du. Y of t is y, and c1x1 plus c2x2 plus and so on cnxn is cx plus d1 u1 plus and so on drur is du. So where y is a column vector of the output variables, y I of t, C is an m into n matrix of the constant coefficients Ci that weight the state variables, and D is an m into r matrix of the constant coefficients Dij that weight the system inputs. And block diagram representation of linear systems described by state equations. A system of order n has an integrators in its block diagram. The derivative of the system variables are the inputs to the integrator blocks, and each state equation expresses a derivative as a sum of weighted state variables and inputs. A detailed block diagram representing a system of order n may be constructed directly from the state and output equations as follows. So here u of t is input and here y of t is output. So first u of t output can give to the b, and again this output is also gives to the d, and from this b it is goes to the x inverse of f, and from s inverse of f it goes to the c, and from also s inverse of f to it again goes to a, and from this a this again goes to this again goes as feedback. So here we can have plus plus, and here we can also have x dot. So from b to s inverse of f you can have x dot, and from s inverse of f to c we can have x, and here here this a is feedback. So from this s inverse of f this it can goes to c, and from this c and this from c, and the d can get addition and it can get as output. So this is the block diagram representation of linear systems described by state equations. And applications of state equations. State equations are widely used in robotics, aerospace and automotive systems. They form the basis for designing controllers such as PID, which is known as proportional integral derivative, and state feedback controllers. Applications also include economic models and biological systems modeling. And the conclusion and future trends are: understanding state equations is fundamental for modern control system engineers. With advancements in computational power, state space methods continue to evolve. Future trends include the integration of machine learning techniques with state space models. This is the conclusion, and this is about my topic. Thank you, sir.